In the previous video we have introduced copper indium gallium diselenide or disulfide as a complex material with good potential for application in solar cells. We have discussed the atomic structure of CIGS and we showed that the type of conductivity depends on the molecularity and non-stoichiometry of the material, being if the material is copper rich or indium rich and if it is selenium rich. In this video, we'll go through two different production processes of high-performance CIGS layers. Secondly, we will introduce the cell structure of a CIGS-based solar cell. The first method to deposit a CIGS layer is called three-stage co-evaporation. Essentially, all the required atoms are evaporated in a single process in three different stages. The highest efficiency solar cell produced with this method in 2016 by the German Research Institute ZSW has an efficiency of 22.6%, making CIGS one of the highest performing thin film technologies. This graph shows the growth rates of the metals on the left-hand y-axis and the selenium rate on the right-hand y-axis versus time of the three-stage co-evaporation process. Prior to the first stage, the rates are ramped up to the required levels. In the first stage, a layer of indium, gallium and selenium is evaporated in the required ratios at a temperature of approximately 400 degrees Celsius. In the second stage, the temperature is ramped up to about 550 degrees Celsius, while both the indium and the gallium evaporation is stopped and the copper rate is increased. This second stage will initiate crystal growth of the CIGS as copper will blend into the porous first layer of indium, gallium and selenium. In the third stage, again a layer of indium and gallium is evaporated in the required ratio while the copper evaporation is stopped. This leaves a relatively copper-poor film on top of the stack, which is favorable for the CIGS crystal formation and improves the interface quality with the buffer layer that is deposited on top, as we will see in a minute. In this way, the polycrystalline film is obtained, which means a layer with crystals of various sizes in various orientations. While the three-stage process is capable of delivering a very high-grade CIGS layer, the industry prefers a fast and sequential process rather than one relatively long process. The second production method is called the two-step precursor and selenization process. Here a copper indium gallium or CIG layer is sputtered on the substrate as a first step, while the selenium atoms are included in a selenization process with a hydrogen selenide gas, which is very toxic, or by selenium vapor. This method is adopted by the Japanese company Solar Frontier, a market leader in this field, and they have reached a conversion efficiency of 22.3% with this two-step process. Now that we have discussed the most commonly adopted production method for the CIGS absorption layer, this figure shows a cross-section of the traditional CIGS solar cell with an absorber layer of about 2 micrometers. The production starts with the back contact. The cell is therefore deposited in substrate configuration. The absorber material is deposited on a soda-lime glass substrate with a molybdenum metal back contact of about 500 nanometer thick. This particular metal is chosen for various reasons. Firstly, its surface morphology has a positive effect on the crystal growth of the CIGS layer. Secondly, it can withstand the expansion and contraction forces by the variation in processing temperature. And thirdly, it is porous for sodium ions. It has been found that a slight contamination of the P-type CIGS with about 0.1% sodium ions results in better passivation of grain boundaries in the material. Sodium can be added in the deposition process or by using a soda-lime glass substrate as a source for the sodium. The P-type CIGS absorber layer is deposited on top of the molybdenum layer while the p-n junction is formed by depositing an n-type CIGS layer such as an indium-gallium rich layer. This forms a so-called buried junction. A cadmium sulfide buffer layer of about 50 nanometers is deposited on top of the absorber layer to provide lattice matching between the CIGS and the transparent conductive oxide layer, or TCO layer. This TCO layer starts with a thin layer of intrinsic zinc oxide to reduce lateral shunts, followed by a thicker n-type aluminium-doped zinc oxide, or AZO layer. Together, they form the transparent front contact of the CIGS solar cell, which is also referred to as the window layer. When we look at the energy band diagram of this cell, we can see that the TCO has a wide band gap of 3.3 electron volts to reduce parasitic absorption. The band gap of CIGS for industrial solar modules is about 1.1 electron volts, while the cadmium sulfide layer has a much wider band gap of 2.5 electron volts. This essentially forms a heterojunction with the p-type CIGS. Band bending close to the cadmium sulfide interface creates a favorable electric field that pulls the electrons towards the p-n junction while repelling the holes to the molybdenum back contact. To summarize this video, we have discussed that co-evaporation of CIGS solar cells resulted in a very promising lab cell conversion efficiency of 22.6% by ZSW as of today. The method of two-stage precursor sputtering followed by selenization is the preferred method by the industry and has proven to yield a very similar efficiency of 22.3% by solar frontier. And finally, we have discussed that in the traditional cell structure, a so-called buried junction exists inside the p-type CIGS absorber layer, which forms a heterojunction with the wider bandgap cadmium sulfide buffer layer.